All right, so without further ado, let's go to our first speaker, Arefeh Farahmandi from University of Tehran, and she is a master student who is going to tell us about modeling the temporal dynamics of neurons in the IT cortex.
Yeah, thanks. I'm Arefeh, and I wanted to speak about temporal dynamic of uh, neurons in the IT cortex. Let me start. And yeah, I think that's okay. Yeah, that's my screen. You can see all. Okay. Let's go. I want to talk about modeling the temporal dynamic of neurons in the IT cortex. Our project is based on experiment which is done on two monkeys. We have a rapid serial visual presentation in our task, and as you can see, we showed monkeys for 100 millisecond blank gray screen. After that, we show our image, which I will explore more fully, and it takes about 300 milliseconds. After that, again, we have a blank gray screen. At the same time, we have electrophysiological recording from IT cortex of those monkeys. And we have different category of image. They are in different abstraction level, because we just want to say wanna see that whether they are encoding in multiple time course of our neural response or not. And as you see, images are divided into different category: animate, inanimate, body, face, and vice versa, which I will explore more in the next slide. Our goal is to design a model which gets our image and produce the neural response, I mean artificial neural response for us. So we do this work into two steps. First of all, we use a pre-trained ResNet. It is combination of convolution layer to extract the feature vector of those image for us. And in the second phase, we use partial least square regression, which use those feature vector of our image and trained by our real neural response. And after that, it can produce our artificial neural response. As you can see, the results are surprisingly great, because we can see here, for example, we have two sample image, and here we have the temporal dynamic neural response of our real neurons, which we record from IT cortex of monkeys. And here we have artificial neural response. As you can see, they are really similar to each other, and that's a really great for us. In the next step, we calculate the correlation between neural response and artificial neural response in different category to see what is the value of correlation. And as you see, we have approximately about 80% correlation in different categories, and this is a really great result for us. In the other step, IT cortex is responsible for categorization. So we expect that our real neural response is able to classify different categories with each other. So we do some bootstrapping and classification on our real neural response to see what is happening. And as you can see, the blue plot is using those real neural response, and it is a normalized accuracy of our classification. 0 shows exact time that we show image for the first time after blank gray screen to the monkeys. And as you see, this is increasing here. It's exactly the time course which our visual information of image is received on our IT cortex. So the accuracy is increasing, and the orange one is our artificial neural response. I mean, it is the accuracy of classification using our artificial neural response. And as you see, its behavior is such a good, because it's also is have this trend, and we do this for different classification. For example, here we have body face classification, here we have animate inanimate classification, and also we can see here that it is our neural response which is able to classify different category, and also we have a little good accuracy for our predict and artificial neural response. In the next step, we have basic level advantage, that it is expected to be observed in our real data. It is our real neural response, and here is artificial neural response. As you can see, in our brain, recent electrophysiological studies have suggested that earlier and later neural phase of neural response can encode multiple hierarchical abstraction of our image and our visual information. So body face is our mid-level abstraction of our visual information, and animate inanimate is superordinate level of abstraction. So we just anticipate that it should be observed that in our artificial neural response, the earlier phase of our neural response is responsible to classify the mid-level of our image. And as you see, this is really great, because we have this observation here, and you can see the peak time of our accuracy in body face is sooner than peak time of superordinate level of abstraction, and it is really similar to our real neural response. So that's really great for us. It's finished, and I'm just here to answer your question.
Thank you. That was wonderful. So if you have questions, please put them in the Q&A session, in the Q&A of Zoom. So we have a first question right now. How did you find the peaks? So Arefeh, can you?
And maybe, yeah, exactly.
Maybe you can keep screen sharing and maybe leave it to one slide that is informative for people who are
I think we can. Okay, about peak. That's a good question, because we just have a lot of methods for calculating the peak, but here I use 90% of our response. The first time which we arrive at 90% of our peak value of plots, we name this time as peak time course of our data. There are different definitions for that, but we use here 90% of peak, the max value of our accuracy. And after that, we just calculate the first time which we can arrive at this point.
All right, thank you. So then the highest upvoted question so far is by Michelle Green. Not clear about how the peaks were. Oh, it just went a little. So not clear how the peaks were found for the basic level advantage for real neurons. They actually look a bit early. Can you?
Can I see the question?
Yeah, so if you click on the
Q&A, I should stop share screen to see the question. Yeah, not clear about how the peaks were found for the basic level advantage for real neuron. They actually look a bit early. I don't know if it's early, but as we investigate about that, we really found that it's about I think about 100 milliseconds after showing the image. So I think that's good, and I don't know if Michelle can explain about it. I think that's really expectable. But I don't know what is the normal range that you mean.
And Michelle, I just allowed you to
Yeah,
talk.
hi. Yeah, what I meant is very similar to the previous question. When you looked at the peaks for the left-hand graph that you were sharing, it looked like the functions of the decoding accuracy kept increasing over time. And so it seemed like the peaks would actually be later on and that the pattern would actually flip, that the animate-inanimate distinction looked like it was a little bit earlier than the face-body distinction for the real neurons, but not for the artificial neurons.
You mean the difference between, let me share my screen. You mean this, yeah?
Yes.
Yeah, that's really that's really strange for me too, because I think it should be like here, yeah. But I don't know. That's our result, and I should work on more. But we have a lot of methods here. I just use 90% of our accuracy, but maybe I can calculate it in the other methods to achieve a better value for my peak. But that was our observation, and yeah, I agree with you, because I just see that, and it was surprising for me, because I really anticipate that it is in this time course.
All right, great. So there was a question that got marked as answered, but actually wasn't addressed. So you have negative accuracy on your axis. I think the issue is that you're showing normalized accuracy. So maybe you can explain a little bit how you normalize the accuracy.
Sure. We calculate normalized accuracy, and it is based on our the accuracy that we have in our baseline, and baseline is defined the time course, the 100 milliseconds after showing image. This accuracy is our baseline accuracy, and we just normalize our accuracy based on this value. I mean, the mean value of accuracy in our baseline time.
All right, wonderful. And one last question that we have, and I think we'll be out of time afterwards, by Zishan Kadir. You mentioned around 0.8 correlation among different categories. How this is advantageous for your classification problem?
It's not beneficial for our classification. It's the first phase of our results, because the goal of our project is to design a neural network that is able to predict and produce the neural response. And after that, we just calculate correlation of artificial neural response with our real neural response to see whether they are correlated with each other or not. And they don't I mean, that's not related to our classification problem. We just use classification to see the categorization of our neural response, because IT cortex is responsible for this task. So we just want to test about our artificial neural response to see if they are true for our artificial neural response either.
All right, so great. There's actually one more question from the chat that I would like to ask you, and I was actually wondering about that myself. So this is from Eugenia Penk. Could you elaborate on how the artificial neural responses were calculated over the time domain? So for the artificial responses, how do you get?
Yeah. You know, as I said, we have two steps. At the first, we just extract the feature vector of those images that we showed to the monkeys, and after that, we use partially least square regression. It gets our feature vector that is a vector, and after that, give us the output of, I mean, the time series of our response. And a regression is able to do this, but in the next step in our project, we just want to inject some dynamics in our ResNet, because in this work we don't have dynamics in our ResNet, but in the next step I just wanted to inject some dynamics. I mean, feature vectors are changing in time course, because the visual information that's received in the IT cortex of mind is changing over the time. So we just wanted to do this work for future.
Wonderful. Thank you, Arefeh. That was great.
Oh, thanks.
So,
thank you. Yeah.
So next up we have Master.